Hello everyone, we are team 134340 and today we would like to present our energy demand forecasting model to you. The reason for us to carry out an energy demand forecasting is to prevent blackouts or erase the capacity, as we believe that the time and power usage are closely correlated as the frequency of human activities varies with time. The first key technique we use is linear interpolation to find the missing data, and the second is that we train a model to make forecasts with neural networks. For the historical datasets, there are two columns, representing the dates and hourly data respectively. To carry out the datasets analysis, we find the persistence RMSE, the key statistics, and we normalize the data in column B. Also, we complete the linear interpolation of the raw dataset to find the missing values. At last, we execute the functions. The next slides will be a clearer procedures. After obtaining the key statistics and hard-coding the mean and SD into the normalization function, we write the data CSV file to store the normalized set score and split the data CSV file into train CSV and test CSV file in a 7:3 ratio. The graphs attached here show our findings.
Moving on to the solution development methodology, our task involved calculating the statistic for the PGM dataset, which include mean and standard deviation. At the right-hand side, you can see the function we used to calculate this. Secondly, we also input the mean and SD into the following equation, and then run the normalized function to update the train and test dataset. Lastly, we predict the power demand at t+5. Of course, we do have a lot of challenges during our journey. We obtained several errors after running our program. To correct this, we learned from our mistake and do a lot more trials. First of all, we benchmark on the lab one and study every single detail of it. And then we also align multiple syntax used and comment the unwanted programs to prevent any unwanted conflict as well. And then we also ensure that we are referring to the correct data set. For example, column A referring to date and time, and then column B referring to historical figures for power demand. And lastly, if all the above methods are not working, we also restart our program and prep the main.m again. Next, we will show you a demonstration video to walk you through our journey.
First, we followed the instructions and prepped the dataset, and then after which we went back to Lab 1's prep M to figure out how to do the statistics function. We first uncommented the stats line, and then we also uncommented the persistence RMSC line. That allowed for the calculation to happen. Then afterwards, we just copied and pasted entire stats coding into Lab 2's prep M, and we changed all the CS into XS in alignment of the syntaxes. We added the range by following the above coding, and then we also went back to Lab 1 to copy the persistence RMSC coding. We checked that it was what we needed, including the syntaxes and whether t+5 was correct. And then afterwards, we just added the encodes targeting B, the power column, which allowed us to generate the result. The first set of results that we've generated failed to change data, test, and train CSV into smaller numbers, and they remained in the 5-digit values. Hence, we retyped the code just to check that we made no mistakes, which subsequently changed data, test, and train CSVs into small numbers, showing that it has been normalized.
The next section is the results. We start by analyzing the loss graph and relevant statistics. We can see that memorization did not occur because the red line representing test loss does not go up as iteration increases. The eventual test loss and training loss are both around 0.03. Since the test loss is smaller than the persistent RMSD, we can conclude that the model is useful for prediction. We then move to the training and testing prediction graphs. Since most of the blue area is covered by the red area, it once again provides evidence that the model is useful for prediction. However, we observe that the model downplays the actual deviation and it is slightly over-conservative.
For the scatter plot, we can see that the performance of the model is consistent because the two graphs shows highly similar patterns, but the correlation between actual and test data is slightly weaker. For the lag plot, we can see that the lag of training and testing are both 4. Although it's still a useful prediction as RMSE is lower than persistent value, but as there's no any peaks at lag equal to 0, the model can still be improved. There are 2 areas of improvement. First, to get a combination of an even smaller test loss, you can change the model with different configurations or adopting a different network. To reduce lag, we can also adopt a dropout ratio and regularization to optimize the training process. So that's the end of our presentation. Thank you.